Okay, good afternoon, everyone, ladies and gentlemen, and geologists, and thanks for making yourself available on a Thursday afternoon. It's been interesting to change the time and see that people have woken up or read Henny's notifications and are pitching up in the afternoon. It's my pleasure to introduce Tarryn Cawood. She's going to talk to us about her experiences of gold deposits in California in the US. And just also a privilege to introduce one of our own. Tarryn grew up here in Hermanus. And it was quite interesting putting her CV together, or biography. We went across the road and spoke to her, one of her old teachers who taught her at junior school. Anyway, we won't go into all of those details, but she did say Tarryn at junior school was a very diligent, quiet, hardworking individual. So good for you, Tarryn. Anyway, Tarryn, again, graduated at Stellenbosch University. She did a BSc there and then her honors degree. And it's interesting that we're having another Stellenbosch person or Stellenbosch graduate give a talk on gold today. We had a very good series a month or two ago, led by Neil Phillips and Alex Kisters. Neil's on the course today, focusing on the really good work that Stellenbosch have done over the years at Barberton in particular. Anyway, after her degree or graduation in Stellenbosch, Tarryn worked as a production and exploration geologist at Black Mountain at Oxidation, and while there she completed an after-hours MSc on the Swartberg deposit. She then went to do a PhD at the University of Southern California in Los Angeles, and there her focus was on the rheology and architecture of the Simplon shear zone in the Swiss-Italian Alps, with side projects on the Oro Cruz gold deposits and the Cuesta do Randolpho shear zone in Argentina. So she certainly got around looking at gold deposits all over the world. During lockdown, she undertook some freelance online consulting work, mostly on exploration targets back at the Oro Cruz deposits in California. And currently, and she's moved across there quite recently, she's working as a postdoc research scientist at the Canadian Geological Survey in Ottawa, where she is investigating how deformation and metamorphism affect the distribution of critical minerals and VMS deposits. So thanks, Tarryn. Thanks for making yourself available and getting up early this morning, and we look forward to your presentation. So you want to go ahead and share your screen? Yeah.
Absolutely. Thank you very much for the introduction and for inviting me here. Let's see if this works.
There you go. That's excellent. Okay. Over to you.
Great. So yeah, thank you everyone for inviting me here. It's really cool presenting to my hometown, even if I'm on the other side of the planet. So as John mentioned, I'll be talking about some work I did on gold mineralization in the far southeast corner of California. And this is work that I did while I was living in that plain Plattelandsdorpie that you guys might have heard of, Los Angeles. And I did it together with several collaborators, all on the American side, Amy Moser, Ariel Borsuk, and Alan Rooney. So some of the work I'll be presenting can be found in this recent paper, like just came out a few weeks ago, which is really exciting. The rest of the work that isn't in here will be published in a paper that I promise I will definitely be writing soon-ish, one day. So if you mention gold in the American West, people tend to think of the wild, wild West, cowboys, Indians, saloons, and all of that. Well, that is exactly where we'll be going for today's presentation. It was quite cool walking around this old Oro Cruz deposit. You actually saw quite a lot of the remains of the old gold rush era towns, but a little bit of like a ghost town feel to it. So here we have a geological map of California on the west coast of America. Just want to check, are my slides progressing properly?
No, it hasn't moved. No.
Okay, we have a problem there. Let me quickly try reshare all of this.
There we go.
Okay, second time lucky. You can tell it's a little while since I've done Zoom presentations. Okay, and are we moving back and forth? How's that going?
Good.
It's fine.
Great. Okay, so that paper I mentioned, here's a picture of it. And then this is the American gold in the Wild West, which is pretty much where we will be working today. And here, there we go. Can everyone see my pointer?
Yes.
Great. So we're starting off with a geological map of California, shown here on the left. And geologically, the American West is also pretty wild. So much tectonic history going on here. The events that affect our story start with the Jurassic to Cretaceous magmatic arc, which is here represented by all these rocks in red. You can see it stretches all up down the coast. And that was related to eastward subduction of the oceanic plate. Then in the late Cretaceous, the subduction angle actually decreased, which shut off arc magmatism and caused the major upper plate compression known as the Laramide orogeny. After that, we had orogenic extensional collapse during the Oligocene Miocene. That's most famous in the Basin and Range province, which pretty much out here, you can see all these kind of stripes. Those are the famous basin and ranges that resulted from this extension. However, this extension affected much of the area, all the way from Canada up there down to Mexico down there. And then finally, as if all of this wasn't quite enough, the oceanic spreading center itself was subducted. And that triggered the switch from the subduction setting that we had previously to a transform margin, which is ongoing today. And today we have much of that dextral strike slip motion of that transform margin is taken up on the famous San Andreas fault, which is this very faint black line running all the way up here. So because that's a lot to remember, I'm going to have this little summary that I've got at the top right, and I'll show this every now and then during the presentation. And all you need to remember in detail is that we started with the magmatic arc, we had an orogeny, it all collapsed, and then we changed to a transform margin. And I'll just keep that up for reference every now and then. And just for reference, the famous mother lode deposits of the California gold rush, those are sitting up here in the foothills of Sierra Nevada. Today, we're actually focusing all the way down here on that little red blob in the far southeast corner of California, right on the Mexico boundary. So if we zoom in, we can see that this area actually boasts a number of gold deposits. Most of them are now inactive, although the mesquite pit up at the top left is still going strong. And in the last few years, there's been quite a bit of exploration out in this region. So it's getting some attention. Where it gets interesting to me is when you realize that just about every deposit on this map has been attributed to a different one of those tectonic events we spoke about. So we can't just come in and apply some general model for all the gold in the area. For example, early work suggested that the American Girl and Padre Madre deposits over here were both deposited by magmatic fluids released by Jurassic plutons, so during that magmatic arc period. However, later work suggested that the gold at American Girl was actually introduced during that late Cretaceous Laramide thrusting. So that event. However, some work on Picacho off to the east suggests that its gold is hosted by a low angle detachment fault, which probably formed during that extensional collapse period. And finally, some work at Mesquite, far off to the west, shows that their gold is hosted by steep dextral strike slip faults, likely related to the young San Andreas type transform margin. So we've pretty much gone through every one of these different tectonic episodes. And we've got a whole host of different tectonic settings to choose from. And that means a whole range of different possible genetic models, each with its own different exploration criteria, which makes working in the area pretty confusing. So we're going to have a quick look at each of these genetic models. Don't worry too much about the diagrams. There's a lot of detail. We won't go into it. They're just pretty much there for illustration. We'll run through these genetic models quickly, and then we'll dive into the work that I've been doing on Oro Cruise. So just briefly, talking about intrusion-related gold deposits. As the name says, these are gold deposits closely associated with apparent intrusion, where a lot of the gold and fluids is thought to come from the late-stage magmatic fluids. These intrusions could be oxidized or reduced, typically granitic or granitoid, and you often have metal zoning away from the the parent intrusion. For example, here you've got this little pink pluton, you have gold close to that, but further away, you'll get your silver, your lead, your zinc, various base metal veins. Then we'll look at orogenic gold deposits. We've got Neil Phillips in the audience, who can tell you everything you need to know about these. So they're typically found in deformed and metamorphosed terrains, and they're not necessarily always associated with an intrusion. They typically form sort of just after the peak metamorphism during the waning stages of orogeny, and they tend to be associated with a change in the regional stress state. They're very definitely structurally hosted deposits, spatially associated with sort of second order structures near to crustal scale first order faults. And the gold is often sitting in quartz veins, but it can also be disseminated or replacement style mineralization, but always with a structural control. And they can form over a wide range of crustal depths from 20 plus up to about 3 kilometers, but most of them form here around the brittle ductile transition, sort of green schist facies depths. So what's that, 10, 15 kilometers. And then in contrast, we have epithermal deposits, which form at much shallower depths. We're talking the upper 1.5 kilometers. And they tend to, again, be associated with magnetism, fluids coming off of those intrusions. And then they're associated with subsurface boiling, hot springs, and a whole suite of funky associated elements. And that differs to the orogenic deposits that we just mentioned, where they tend to have very simple elements, very clean. You'll have gold, you'll have 1 or 2 sulfides, and not much else. Whereas here in the epithermal, you're going to have antimony, arsenic, mercury, all sorts of things. Right, on to our cruise work. So for the study, I broke it down into 2 main missions. Mission number 1, figure out the geological history of the Orocruz deposit and the area surrounding the magmatism, the deformation, the alteration, and put that all into a geological timeline. And then mission number 2 is figure out which units or which structures or which alteration assemblages are associated with that goal. Once we've succeeded in those 2 missions, we can put all of that together to come up with a genetic model and eventually exploration criteria. So we're now going to zoom in on that tiny red blob that we saw on the California map. These are the Cargo Muchacho Mountains. And the name literally is Spanish for loaded boys. And it's from way back when the area was first kind of discovered by Spanish moving through it. I think they were herders. And they got to these mountains, hung out in one of the valleys. The kids went off to go play and came back with their shirts kind of holding up all the piles of gold nuggets that they had found. So the boys came back pretty loaded. So these mountains are predominantly made up of Jurassic magmatic arc material. So it's all rocks that formed during that magmatic arc event. And these include the volcaniclastic Tunco Formation, which is this kind of bluey green color. And this was then intruded by slightly younger, but still Jurassic plutons, which are shown in the orange, the purple, and the pink. These are all granites to granodiorites. All of these rocks were then deformed and sheared to some degree while at amphibolite facies conditions. So they're all hot and squashed. We're now going to zoom in a bit further to the Orocruz deposit itself, sitting right there in the Tunco Formation, very close to the contact with this granite. Here we have an oblique aerial view of the Orocruz pit. You can see the dirt roads going over here just for some scale, the main access running down into the pit over here, and you can see several benches going up the sidewall over there. So mineralization occurs in these kind of stacked diffuse zones, typically marked by a distinctive red to blue iron copper staining. And I've outlined those with the blue and the dark red over here. These zones dip gently to the southeast, so kind of the top left of this image, and that is parallel to both the main ductile foliation and the main low-angle brittle fault that's exposed in the pit, shown here in the brighter red. This is just more of a cross-sectional view showing the same thing. You can see that low-angle brittle fault running down here, the mineralized zones, blue and reddish over here and here. And you can also see the abundant pegmatites, all of the white stuff in the underlying image. Those are all pegmatites. quite spectacular in person. So to kick off mission number 1, let's take a closer look at that regional ductile foliation. So if we look under the microscope, there's a photomicrograph at the top right. You can see that that foliation is associated with high temperature quartz microstructures. We've got chessboard extinction at the top right, these really wiggly grain boundaries typical of unrestrained grain boundary migration. And these microstructures, together with the fact that I've seen ductile feldspars, suggest deformation at temperatures around 500 degrees Celsius. So this is pretty warm. Then, although shear sense indicators are quite rare, we do have occasional sigma clasts, like this green epidote blob. You can see how it's been smeared out asymmetrically. And they suggest top to the north-northwest sense thrusting. And finally, within the high temperature thrust foliation, in that nearby granite, we have titanite. We've got both these nice euhedral magmatic titanite crystals shown at the top left. And we also have these little clusters of titanite crystals that look like they've been dynamically recrystallized. Now, this is really cool because you can date titanite by analyzing its uranium and its lead contents, but that date might be reset. So my collaborator, Amy Moser, is a titanite genius. She went and dated a whole lot of our titanites and found these 2 age populations showing on this plot in the bottom left. The magmatic titanites yield a Jurassic age. And that's what that makes sense. They probably grew when the protons were in place as part of that Jurassic arc. So cool. However, all those titanites that looked like they were deformed, well, they consistently gave a late Cretaceous age of about 68 million years, which we interpret as the age of this high temperature ductile thrusting event that caused them to become dynamically recrystallized. So that's really cool. We know that this shearing event happened around 68 million years ago. Now we're going to have a look at all of those spectacular pigmatites. So as you can see in the top right, pigmatites that are subparallel to the ductile foliation are commonly boudinaged. They've been stretched out. While those at high angles in the bottom photo are folded, so they've been squashed. And if we look at a schematic strain ellipse over here, we can see that this is compatible with top to the north-northwest directed thrusting, during which you'd have regions of elongation, roughly parallel to your foliation, and regions of compression perpendicular to it. Cool, so these pigmatites must have intruded either before or during that ductile thrusting event, and were then deformed by it. My other collaborator, Ariel Borsuk, dated several of these pigmatites by zircon uranium lead analysis, and found, surprise, surprise, a late Cretaceous age of 63 to 65 million years for different pigmatites. And just for interest, these images here show what the zircons look like under a normal light microscope, and these are CL cathodoluminescence images. And if you're used to looking at zircons, you can tell straight away that these look pretty messed up, and that's because they're highly, highly metamixed. And that's because of their high uranium contents, which is typical of pigmatites or other evolved melts. So it all kind of fits together. Now we're going to have a look at the brittle faults. So as noted earlier, we had that main brittle fault exposed in the pit, which is the one shown here with a rather tall geologist to scale over there. It's a low angle structure, pretty much parallel to the high temperature foliation, which seems to just be reusing that plane of weakness. And it seems to have, at least here, top to the north thrust sets. However, we haven't really got lineations on this at the moment, so we're not exactly sure of the thrust sense here, of the kinematics. Now, sadly, we don't have direct age constraints on the brittle faults, but we do have uranium-lead cooling ages from magmatic apatite in the pigmatites and the granite. And that's apatite grains that I have shown here. You can actually see the analytical spots, which is quite cool. And the uranium-lead cooling ages from these suggest that the area cooled down to below 450, 500 degrees sometime after 60 million years ago. And that relates to the faults because these faults are very clearly brittle, so they must have formed at a lower temperature, and thus at some later time. We're not sure when, but it was sometime after 60 million years. Okay, that's it for structure. So you can breathe a sigh of relief, you got through it. We're now going to have a quick look at some of the cool alteration assemblages visible in the pits. And there's some really spectacular stuff. So we start off with some narrow magnetite quartz veins, which you can see in this photomicrograph here. It's pretty much a pure quartz vein with magnetite all along the edges. And they can either be highly folded, as you can see here, or in this photograph on the left, or smeared out parallel to the high temperature foliation. And which, again, we reckon they're either pre or syn ductile thrusting. We also have really beautiful epidote-rich alteration, sometimes with quartz, often with hornblende. You can see the dark green hornblende here, reddish garnets, and sometimes minor calcite. This alteration style is also sometimes associated with magnetite, so it might be related to that same hydrothermal event as the magnetite quartz veins. And we also interpret this as pre to likely syn ductile thrusting based on its textures and structures. Then, if you look very, very carefully, you'll find the rare alteration assemblage, the sulfides, pyrite and chalcopyrite. These sulfides occur disseminated within the foliation. On the left photo, you can see these scattered little sparkles of pyrite and chalcopyrite. And they are always closely associated with the folded magnetite quartz veins. Here you can see those running all over here, the white-gray shapes. However, not all areas of magnetite quartz veins have sulfides. Just a point to keep in mind for later. And at the bottom right, we have a reflected light thin section photo, and you can see the gray magnetite and the sort of shiny gold-colored pyrite that appears to be overgrowing the magnetite. Now, this could indicate that they were precipitated together, both during that high temperature thrusting event, or that the sulfides were introduced later, maybe even much later, maybe even during brittle faulting, who knows? And they just preferentially precipitated where the fluids reacted with magnetite. So from the textures alone, we can't easily distinguish between these two options, but we can date the sulfides. And this I did with Professor Alan Rooney at Yale, using rhenium osmium, which is a really cool method. You can't do it in situ, you have to do the full wet chemistry thing, which as a structural field geologist, they don't often get to boil my samples in acid, which was quite fun. And our rhenium osmium data yields an age of, you guessed it, 65 million years. So it looks like these sulfides were brought in during that ductile thrusting event, and not later during the much younger brittle faulting. Now, the last assemblage that we're going to look at is the oxidation. So this is really widespread in the pits. We get this late supergene oxidation. It affects both the magnetite and the sulfides, forming red iron oxides, basically rust, as well as blue and green chrysocolla and malachite staining. And it's spatially associated with brittle faults. We've got the main brittle fault running through this photograph, and that's where the most intense oxidation is. And it's also associated with like late fractures and joints. This photomicrograph actually shows fractures filled with chrysocolla that are cross-cutting high temperature dynamically recrystallized quartz. It's kind of a cool juxtaposition. So because of this association with the brittle structures, we know that the supergene oxidation happened sometime after 60 million years, when the brittle faulting happened or later. So we can't really constrain it better than that at the moment. Right, so putting all of that together, we can summarize the main geological events recorded in the area. Here, we have the granite, shown in pink, which is thrusted to the north-northwest over the Tumco Formation, blue. We know from previous work that the granite units and the Tumco Formation are both Jurassic in age, so quite a bit older. However, this ductile shearing that created all of this ductile foliation shown with the dashed lines, this was active at around 68 million years ago, when our titanite was recrystallized. However, it was still active around 63 to 65 million years ago, when those synclimatic pigmatites were in place. At around the same time, we have our sulfides precipitated onto the magnetite quartz veins. That all happened at like high temperatures, 500 degrees, but by 60 million years, the rocks had started to cool, And that's based on apatite ages, from apatite in the granites and in the pegmatites. We can also summarize all of the same things in a timeline. This is going from oldest on the left to youngest on the right, just with different events shown on the y-axis. We start off with deposition and replacement of those Jurassic host rocks. That's all during the Jurassic over here. Then we get to all that juicy late Cretaceous stuff that we've dated and figured out. The high temperature ductile thrusting, the hydrothermal alteration, the pegmatite emplacements, all perfectly coinciding with published age ranges for the Laramide orogeny. Then, a few million years later, our rocks have cooled to below 455 degrees, and at some point later, they are cut by a variety of brittle faults. We don't really have times for those, but we know that they're somewhere out here. That's all fine and well, but key question, where is the gold? So I did some assay work that suggested that significant gold grades are associated with the really oxidized material. Here we're just looking at one of the side walls of the pit again. We've got that late brittle fault running through here with a lot of oxidation. And one of the samples here has 7.2 ppm gold. There's a photo of it in the field up on the top right. However, these blue areas, they outline places where there is some oxidation, but some of that material is also still quite fresh sulfides, magnetite quartz veins, and they all still run with gold. Not spectacular, but it's there. This is just a picture looking at the other pit wall, and again, you can see some of the grades close to that brittle fault can get quite spectacular. We're not talking Barberton visible gold spectacular, but out here, these are pretty good. Now we're having a closer look at some of that oxidized material from along the low angle brittle fault. On the far left, we have a whole thin section scan in plain polarized light. All of this dark material here is iron oxide. It's a total mush. On the right, it's just a backscatter image of the same area. So we subjected this to the chem scan, and the chem scan automatically picks out everywhere that it detects gold. You can see, well, firstly, there's quite a lot. And secondly, it's mostly around those iron oxides. The chem scan also produces a phase map. So here we've colored all those iron oxides in blue for some reason, and the iron-bearing clays in green. So you can tell it's all mushy, iron, rusted stuff. Here you can see there's a nice hand sample of that oxidized mush. You can actually see little cubic iron oxide pseudomorphs after pyrites. That's really cool. It was a beautiful, perfect little pyrite cube that just got rusted in place, kept its shape. And the chunk adjacent to this rock actually assayed at 9 ppm gold. So this is good stuff. Here on the right, we have one of those little X pyrites in thin section. And yep, we can actually see some gold. So this association of gold with oxidized material, low angle brittle faults, it sounds a lot like the descriptions of the detachment hosted gold deposits in the area, like that nearby Picacho deposit that we mentioned at the beginning. However, we also saw gold grades associated with that fresh, non-oxidized sulfide magnetite quartz vein material. Here, we're having a look at a much fresher sample away from the messed up brittle fault. And you can actually see here, this is one of those really folded magnetite quartz veins running all over here. The fine-grained black opaque material along the edges is magnetite. And the coarse-grained blobs are mostly pyrite, a little bit of chalcopyrite. And again, you can see we've got gold electrum associated with those sulfides posted right here in the pyrites. Here we have another picture, photomicrograph of pyrites with a nice blob of gold right in the middle of it. That's very cool. And this sample's neighbor yielded 4.5 ppm gold, so still good. And this association, gold with fresh sulfides, quartz veins, posted by a high temperature ductile fabric, this sounds a lot like deposits described as Laramide thrust-hosted orogenic gold deposits, like the idea of that American Girl deposit that we saw at the beginning, and also like described what they call the Caborca orogenic gold belt, which is a whole belt of these deposits running through Mexico. Interesting. before we go on, I just want to show you one or two more textures to do with these sulfides. So earlier we saw this one with the pyrite that seems to be overgrowing the magnetite. And here we have another picture of magnetite again. The colors are a bit different, but it's mostly magnetite. Some of it's oxidized to hematite. But it has lots of these little speckles and blobs of chalcopyrite and pyrite that look like local sulfidation or replacements of it. So, which one is it? Is our gold low-angle detachment style gold coming in the brittle faults, or is it high-temperature orogenic gold coming in the ductile thrust? Well, our interpretation is that the primary gold mineralization was introduced here, together with the sulfides, which we dated during the Laramide erosion. We probably had gold and sulfur-bearing fluids moving up through that ductile shear zone, the major crustal scale structure. Then, when they reached those magnetite quartz veins, which are probably only a little bit older, the sulfur reacted with the magnetites to form pyrites. Because that sulfur was the only thing keeping the gold in the fluids, taking the sulfur out meant dropping that gold, and that's what formed our deposit. However, later, parts of the ductile shear zone were reactivated by that low temperature brittle faulting. And at that time, oxidizing fluids moved along those faults and almost completely altered the mineralization, totally rusted it. And this might have remobilized and maybe even upgraded the gold. Maybe that's why we have the highest grades associated with the brittle fault. What does this mean for that whole mess of models that we saw at the beginning? Well, at least we know Orocruz was not formed by magmatic fluids during the Jurassic because the gold was much, much, much younger than the Jurassic host rocks. Instead, we have several lines of evidence that put it firmly during the late Cretaceous as a thrust-hosted orogenic gold deposit formed during the Laramide orogeny. However, it did undergo structural reactivation and alteration during later brittle events, giving it an overprint that looks an awful lot like these models. If we try to put this into a regional context, here we have a map. We've just kind of moved a bit south. California's, you can just see the corner of it here. There we have Arizona, you can go gambling up there, and Mexico down here. So that Caborca orogenic gold belt I mentioned, well, Epigorary and others reckon it stretches all here through the Sonora region of Mexico, and they are all thrust-hosted orogenic deposits formed during the late Cretaceous Laramide. My work supports the idea of extending this belt to this area. Orocruz is right about there. So cool, this is all part of the same belt. However, also suggests that the deposits up here, which most people have given other genetic models to, brittle detachment hosted or transform fault hosted, well, I suspect they were all part of the same orogenic gold belt. But up here, they've been overprinted, reactivated, maybe remobilized, make them look like supergene epigenetic low temperature deposits associated with brittle faults. And now, just to kind of bring this back to South Africa and do a little bit of a comparison, I've just done a quick comparison between Orocruz and the Shavafordview complex. This is all based on Caitlin and Alex's recent paper. Caitlin, you'll be able to tell me how much of this I'm making up or not, because you know that area far better than I do. But just in short, is there structural control? Yes to both of them. Is the gold younger than the host rock? Yes to both of them. Mineralization assemblage, they start differing a bit. At Orocruz, we've got gold and sulfides, very minor quartz, but then those slightly earlier magnetite, epidote, hornblende, garnet assemblages, which look a lot like skarn. However, at Shavafordview, up in the Barberton Gold Belt, Greenstone Belt, we've got gold, quartz, carbonate with little bits of sulfide lodes and veins. The host lithologies also differ. At Orocruz, we have a metavolcaniclastic gneiss that's actually been metamorphosed to amphibolite facies. And it looks like that gold was probably precipitated at those high temperatures too. In contrast, at Shavafordview, the gold is hosted by clastic metasediments. They've been metamorphosed to lower green schist facies, and the gold was emplaced during sort of mostly brittle deformation. So it must have been below 250, 300 degrees Celsius, sort of ambient temperature. Probable mechanism of gold precipitation also differs. At Orocruz, gold was dropped out because of sulfidation of that earlier magnetite, probably. Whereas at Shavafordview, the gold was likely precipitated due to rapid, drastic fluid pressure drops during fault valve action. Because of all of this, the host structure is also going to be fairly different. At Orocruz, we just have one broad thrust sense ductile shear zone. Shavafordview, we've got a whole variety of different structures and orientations, but they're all associated with flexural slip folding, locking up of those folds, brittle faulting to accommodate that. And the gold is associated with those sort of bedding planes, lithological contacts associated with all of that complex mess, which is really interesting. If you haven't read it, go read Jones and Crystal's 2020. It's a very cool paper. But all of that brings us to genetic models. Orocruz, I reckon it's an orogenic gold deposit associated with deformation and metamorphism, fairly simple mineralogy. Other than the pigmatites, which opens up an interesting kind of worms, there's no magnetism in the area at the time. However, it is quite a high temperature orogenic gold deposit, which might be why its associated assemblage looks like scarring more than anything else. And it does have that low temperature brittle overprints, which really messes things up. In contrast, Shavafordview are pretty typical Archean lode gold style deposits, which are pretty typical orogenic gold deposits. However, I'm really keen to discuss this further if anyone has points to note. With that, I just want to thank the various funding agencies and research spaces that made this possible, as well as Southern Empire Resources and Lincoln Mining, the mining exploration companies that gave me access to the area and just great conversations. And huge thanks to all the people who I dragged out into the field to help me. And with that, I'll take any questions.
Thanks, Caitlin. Right, do you want to unshare so we can get everyone on the screen?
As soon as I can find where on earth my Zoom went to.
In the meantime, Andy, do you want to kick off the questions? Andy Clay.
Yeah, just Tarryn's very interesting presentation. But my question is, what links are there to the original sedimentary sequences, and in particular carbonates, that have now all been graunched up into the sort of mess you're dealing with?
Okay. Interesting question. Also, sorry, can the host please enable my video for a second? I seem to not be able to start it.
Just a moment.
No problem. So Andy, in terms of carbonates in the host sequence, very difficult to identify because they've all been, awesome. Thank you very much. Because it's been metamorphosed these amphibolite passive conditions. In the Cargo Muchacho Mountains, we don't see any marbles or anything that's like super obviously a metamorphosed carbonate. There might have been small amounts of carbonates in that metavolcanic clastic sequence that have just been mostly devolatilized and kind of hidden. The kind of skarn-like assemblage that could be interpreted as like, oh, metamorphosed carbonates, but it's so structurally controlled that either it's completely smeared out, or my interpretation is that those are due to hydrothermal fluids that came in and affected it.
Yeah, I guess my question is really sort of looking at where the source of sulfates. Anyway,
fascinating,
thanks.
and unfortunately I don't know. Like,
Thanks.
I think the sulfur came in with the fluids. Your gold fluids often carry the gold as bisulfide complexes, so your sulfur is being introduced during all the drama.
I was actually anxious to see some of the gold nuggets, not specks in the microscope.
Me too, me too.
Neil Phillips, do you want to join the discussion and comments?
Why not?
Yeah.
Tarryn, well done. I like your story. It was well presented.
Thank you very
the
much.
part I really liked was the way you separated out your higher temperature and later events. Would you have any thought whether your later event, the supergene, would compare to what we call weathering or the regolith in, say, Australian terms, paleo weathering?
Gotcha. Quite possibly. Like in this case, it's again very structurally controlled. So I think it was happening when those rocks were still, like, it's not just surface weathering that we're looking at. So it's not just associated with the paleo surface. It's very much along the brittle faults, along joints and fractures. But it was probably when everything was quite shallow, and it could quite possibly have been due to just normal oxidizing meteoric water. So same process as you'd see right on surface, just infiltrating a little bit further down.
Because when those processes get going, they are very easy at moving gold around and forming higher grade and lower grade areas. But the other thing, they also tend to make the gold more gold rich, if that makes sense. And you showed electrum in the early, and you called it gold later, which presumably means there's less silver later, which would make sense.
That's a really interesting point to look into. So the gold versus electrum was just the ChemScan's automatic kind of designation. So I don't know how accurate it was in terms of picking up silver content. I'd love to go back and actually analyze those gold spots that we found to see, you know, is it significantly higher silver in the early stuff and then more pure gold in the late? But that's a really interesting point to keep in mind. Thanks.
Maybe we can make contact later. I'll point you to one or two papers on people who have worked on that separation of gold grain composition.
Okay, that'll be awesome. Thank you. I should also just do a huge thank you now, because when I started all of this work, my first move was to go to all the papers that you'd given us during my honors course on gold mineralization and refresh all of that and refresh the devolatilization model and all of those things. So huge thank you.
That's one person out of 100 who actually listens and reads things.
So you got it right sometimes, Neil. Okay, well done to both. Just a question to both of you, Tarryn and Neil. I mean, we all hear a lot about obviously gold in Nevada, and I think I'm right in saying that the US is about the 4th largest producer of gold in the world. And I mean, these little deposits that you're talking about in California, and I don't mean to demean them, but what's the difference between the sort of geology and the gold development in these types of deposits versus, you know, I guess the super sort of gold deposits of Carlin Trend and that, you know, what are the sort of main differentiators between the two? And is Nevada sort of the biggest producer in the US?
No, John, you
ladies first.
Thanks. Absolutely, yeah. These deposits down in the southeast, completely different tectonic setting, model, everything. They tend to be much smaller, locally high grade, but they're not huge. It's not going to be the next Nevada. Yeah, your Nevada Carlin style gold deposits tend to be much bigger. A lot less nice to look at because it's all this horrible, very fine-grained invisible pyrite with even more invisible gold. So less fun to do field work in. But yeah, your Carlin deposits will have much bigger grades, much bigger footprints, much bigger systems overall.
Just on that, John, I wouldn't underestimate the importance of mesquite. Mesquite was in Tarryn's top left corner, and you didn't say much about it, but I think your work could easily flow across there to help them interpret mesquite. And mesquite's an important deposit, and when you look at your map, there's an awful lot of cover and no outcrop north and west of there. Who knows how many Carlins are under that?
And in a nutshell, what's the model in the Carlin trend or those deposits, Neil, and what age compared to these young ages or Tarryn?
Their host rocks tend to be Ordovician, Silurian, Devonian, and the majority of people want it to be about 34 million years coinciding with some magmatic event. Does it? I wouldn't try and translate that across to this work.
Yeah, unfortunately not. And I think it's, Neil, correct me if I'm wrong here, but I think the Carlin deposits, you tend to have, again, a bit of carbonate in those metasediments that are the host rocks. And instead of this really focused, just fluid flow along one structure that we have here, you've got very diffuse sort of basin scale fluid flow reacting with the carbonate in those sediments. And that's where you end up with these huge areas of mineralization. But yeah, that's, I think, like say about 20, 30 million years old, related to the much later orogenic collapse, regional extension, magnetism story, whereas this is the earlier orogenic compression episode.
Yeah, thanks. Okay. Caitlin, your contribution as another gold expert or another young gold expert.
Hi, sorry, can you guys see me? Hi, Tarryn, it's lovely to meet you. No, I don't have much to say. I just want to say it's really cool to see the comparison between your work in California compared to, you know, just here in Barbados and Mpumalanga. So yeah, lovely to meet you, and thank you for the mention as well.
Yeah, good to meet you too.
Thanks.
And how's it going in industry, Caitlin? Are you earning your monthly salary yet?
Yes, not too bad. We were actually supposed to go up to the Congo now. That unfortunately got cancelled due to some visa complications. But otherwise, it's been good. Really trying to figure out, you know, really what's going on with 3D modeling. But I sort of have my grips to most of it now. Otherwise, I can't complain. It's lovely earning a salary compared to being a student.
Good. We're glad to hear that. Okay, more questions. Anyone else?
I can just jump in with one quick thought. Neil, you mentioned mesquite in their model. So I'd actually been chatting to some of the guys working at mesquite over the last few years, and there's that one paper that's published saying all of their gold is hosted by these steep dextral strike slip faults, San Andreas type things. But chatting to the people on the mine and in the area, it sounds like they agree that that could be the later remobilization and upgrading. So my suspicion is that it's the same as Orocruz, where you had the earlier laramide orogenic gold coming in, and then your later brittle events just remobilized, upgraded it. And that's what they're seeing there now.
Sounds sensible to me.
And how do you manage to get such precise ages out of such shitty zircons? I mean, Erica, would you approve of those ages?
Lots and lots and lots of analyses, and yeah, we had no idea if the analyses would work, but it turned out that the really messy metamixed areas were just rich in common lead. So instead of treating them like a zircon and just trusting the age, we treated them like a titanite or a mineral or an apatite that incorporates common lead and actually have to regress an isochron. And that then gets you to like an original age, excluding that common lead.
So, and that was conventional dating. It wasn't laser ICP or anything like that.
Laser ICP, yeah.
Okay, so I mean, you can get to spots in the better parts of the zircon. Okay.
Unfortunately, I'd have to look a lot more closely at the data. I couldn't catch all the plus minuses on the screen.
Okay, we'll let you off this time. Right. Any other questions? Karen, do you approve of your daughter?
Hairy question, eh, Tarryn?
Don't worry, Mom. You can tell me afterwards.
I think she could be proud of you. Look, if we're starting to wrap up now, guys, I also want to remind you, next week we'll be going down to the normal times. You're going to have to either get up very early or you're going to watch this on YouTube afterwards. But Graham Gavin is coming to tell us about how we haven't even started the gold mining in South Africa in his point of view. So let's see where this great untapped source of gold is that Gavin is going to give us next week at the normal slot of 10:30 if Eskom allows us. Even if they don't, we will soldier on. So see you guys next Thursday then.
Yeah, so Graham's going to talk about all of those gold deposits that Neil Phillips and the rest of our sort of esteemed gold geologists in South Africa missed. Is that right, Graham?
He's not on at the moment. He's dropped off. But I've just been on the phone with him now. He says he's ready to give us the whole story next week.
Thanks, Tarryn. That was excellent. And we look forward to more in the future. And good luck with your new endeavors in the Canadian Geological Survey. I'm sure you'll have fun working there. They're a pretty smart, organized bunch.
Cool. Thank you very much. And thank you guys for having me.
Thank you very much. Goodbye, everybody.